Swayam Prabha. Digital India. Educated India.
Welcome to 12th lecture of video course on tribology. Today's topic is boundary lubrication. It appears from the name itself, the boundary is a marginal. You can say it's a marginal between dry lubrication and full film lubrication. Lubricant is present on the surface, but not that much, which can reduce friction substantially, wear substantially. There will be reduction in friction, there will be reduction in wear, but it will be more than what we get in full film lubrication. So, it is not true lubrication as such, but in many situations under high load, low speed condition and high temperature condition, this kind of lubrication mechanism will occur. Sometimes it occurs at the start when the component is totally new. The surface roughness of the component is very high. During that time, boundary lubrication will occur. So, end of this lecture, we will cover one case study on that, show that initially wear rate is high and subsequently it comes down. As in the last lecture, we discussed there are two modes of boundary lubrication. One is physical attraction or physical attachment of lubricant layer on the surface. Another one is a chemical attachment. Chemical attachment is more like corrosion, what we use a word as sacrificial layer, while physical absorption is nothing like a sacrificial layer. It is attachment and detachment. Because of the molecular attraction, the lubricant will get attached to the surface, and at high temperature it will get detached, or under sliding condition it will be disrupted or it will be detached from the surface. As the first line says, this is known as a physisorption, or attraction occurs because of the van der Waals forces. This figure clearly indicates that the lubricant thickness itself is a 2 nanometer. It is very thin layer. Many times oxide layer on the surface is more than this layer. In reality, every metal is subjected to boundary lubrication, even in absence of liquid lubricant or in absence of boundary additive lubricants. That is a natural phenomena. If material is open to environment, it will get oxidized, a thin layer will be made, and thin layer will not be having very good chemical affinity towards other metal. So, it will give the interface much lower shear strength interface. While in this case, this sketch shows that this is the polar end O shape or a circle shape, this is the tail. As in my previous lecture I mentioned, this tail helps us as a carpet. If you walk on this carpet, it will simply bend. It comes back to the original position when you move away. Same thing with the surfaces. If surface comes in contact with this layer, this thin cantilever bends easily elastically, and the surface is surface passed away, then it will come back to the original shape. Sometimes we use a word as oiliness additives, it stick to the surface. Now, what is the theme behind, what is the physics behind this? It says that energy will be lowered whenever a molecule, whenever this additives is absorbed on the surface, overall energy will come down. That means, you need to provide some energy to remove this layer. That energy may be thermal energy, may be mechanical energy, but you have to provide to remove this layer, and that is why there is advantages. it reduces the overall energy, it brings some equilibrium. However, we say many times that attachment and detachment is a continuous process, but nothing is going to get damaged on that if it is under normal load and normal speed. We are not talking about the severe load and severe speed. In that situation, it will not get any problem, it will not get damaged. It will only detach from the surface, and after some time it will come back and attach. So, it is a continuous process. We need not change a lubricant oil frequently if that is a situation, if that is a mechanism. This slide was shown also in the last lecture. We say that when we want a physical attraction, then it need to have some properties. First thing is that it should get dissolved in solid. If it is not able to adjust with the lubricating oil, it is not able to get mixed with the lubricant oil, then we cannot use that lubricant additive. Another thing we say that with attachment and detachment is generally encouraged by the dilute concentration. The concentration is lower, then it will be frequent phenomena. However, if the concentration is higher, there are many molecules available for the few sites, then even though attachment and detachment may be continuous process, but it will not reflect in the experiments. We will not be able to find much difference in coefficient of friction, much difference in wear rate. This table indicated if we do not use any additives, any boundary additives. In this case, we took example of oleic acid, which is one of the boundary additives having oiliness properties. If it is operated, or tribo surface is operated with a pure mineral oil, no additives in that, simple base oil, the coefficient of friction, estimated coefficient of friction was 0.36. I am using the word estimation because we can never get exact value of coefficient of friction. It is only an estimation. It will having some sort of probability. When we add 2% of oleic acid, we can find the substantial change in coefficient of friction from 0.36 to 0.25. That is a substantial change. But after that, increasing oleic acid is not going to change significantly. So, that is why we require little bit of boundary additives to get favorable results. We do not require complete oil to be boundary additives, because that will be very viscous, difficult to pump, difficult to move. That is why we do not use 100% unless until it is required from the situation. This figure shows how the coefficient of friction varies for different oil and oil additives. The A figure is shows clearly that with the increase in the temperature, viscosity decreases. The decrease in viscosity, coefficient of friction also will decrease. But it after certain temperature, what we know as a critical temperature, after critical temperature it will get unbound, coefficient of friction is going to increase continuously, assuming or treating that lubricant is completely removed from the surface. Even though lubricant remain there, but it will not be effective interlocked at the interface. That is a E curve, which is a paraffin based. However, if you use boundary additives of fatty acid as a boundary additives, then coefficient of friction is increasing after certain temperature, and that critical temperature is greater than critical temperature for paraffin oil. However, when it reacts with a copper, it makes some chemical layer. It is corroding the copper, making some boundary additive layer. Then this temperature is increasing substantially. From here, maybe say it is around 70 degree, 80 degree, it may reach 150, 140 degree. Similarly, for other oils, it can change different, it can show different behavior. Why it is happening with the temperature, why this kind of phenomena is happening, that can be explained using these two sketches. Here it shows that ordered film on the substrate or substance, and it is below critical temperature. Almost all the sites are occupied. surface is not free from this molecule. However, if the temperature increases, then thermal forces will be on higher order compared to van der Waals forces. So, molecular attraction will come down. Obviously, that relative molecular attraction will come down, or relative force will be lesser compared to thermal forces, and we will be getting disordered lubricant lubricant film on the surface. That is the reason why we do not get very good performance at high temperature or temperature above critical temperature. In that situation, we need to think that lubricating oil should satisfy our requirement. If we know the operating temperature is high, then we need to choose proper lubricant additive. It will not that whatever you choose lubricant additive, it is going to survive, it will work. It works only after works below some critical temperature, it does not work beyond that. And it is known that this kind of thermal equilibrium can be estimated, or it can be gauged using the Gibbs free energy. As I mentioned in the last lecture, that Gibbs free energy is more like potential energy. You require some energy to remove this lubricant layer from the surface, and that Gibbs energy can be estimated using this relation. This clearly says as the temperature increases, Gibbs energy is going to go down. If Gibbs energy is lesser, that means you need to supply lesser energy to disturb the lubricant film. If this energy is more, then you require more energy to disturb the film, or it will be more stable compared to stability at the high temperature. That is why it says that at high temperature it is getting deabsorbed, and that is shown again through this figure which we showed in the previous slide. When it is disrupted, then what will happen, surface can easily push this lubricant or lubricant molecules from the surface, leave surface without lubricant layer, where it will increase in this situation. Temperature, obviously as the temperature increases, where it will increase when we are treating or when we are using boundary additives, but that is not 100% true. Few lubricants, they work at the high temperature, they do not work at the low temperature. You may get very high coefficient of friction at the low temperature, but when you go for high temperature, when you operate at those lubricant additives at high temperature, coefficient of friction will come down. That is generally known as extreme pressure additives, or additives which work with chemical action, or they react with the surface. They make some product, they corrode the surface, they make sacrificial layer, but they protect the surface or reduce the coefficient of friction compared to dry friction or compared to unstable film. So, we can study that. We say the chemisorption is happening because of chemical action, and as the first line indicates, because physically adsorbed boundary lubricant or boundary additives either will get detached, decompose or melt. Any of the situation is possible. It can get detached because of the very low molecular attraction compared to their thermal forces. It can decompose also. It is quite possible they get detached as well as decompose. Decompose means a long molecular arrangement, structure gets broken, and it may melt also. It can change its state from solid to semi-solid to liquid, or completely distort the chemical structure. Anything is possible. That is why we require chemisorption at the high temperature, and as I mentioned earlier, that it is a form of corrosion. We are doing purposefully, we are introducing corrosion purposefully. So, to make this kind of boundary layer, what we require? We require a chemically active group. It is something chlorine, sulfur, phosphorus, they are chemically active. If you leave these chemicals along with the metals, they will make some chemical reagent on the metal surface, which will be having a low coefficient of friction and low wear rate compared to metal surface itself. So, this is a chemical active group. In addition, we require a reactive surface of material. All the metals have a reactive surface by and large. Ceramics, they do not have that much, or polymers, they do not have that much reactive surface. So, chemical additives will be useful only for the metals, or by and large for the metals, not be very effective for ceramics, not very effective for the polymers. Or another word, chemical composition required for the metals will be different than chemical composition which is required for ceramic materials, for polymer materials. And there is another one guideline given over here. He said that try to use both the process, physical absorption as well as chemical absorption. Both are possible. If I choose a surface which is chemically as well as physically acting with the lubricant additives, then I can get good results. At a low temperature, physical attachment; at a high temperature, chemical attachments. Same lubricant additives can be used. That is why we can show with the diagram. You see the physical absorption below one critical temperature. This blue color line I am showing as a temperature line, or from left to right I am trying to show this temperature is going to increase. At the low temperature, physical absorption is sufficient. At the high temperature, chemical absorption is sufficient. And there is always a gap between. We generally they do not overlap. Reason being, if there is a physical absorption, if there is a lubricant layer already there, then chemical absorption will not happen unless it is clean completely. If there is something already on the surface, it will not be reactive towards the chemical active group. So, there is need to be some gap, and that gap is known as a temperature distress gap. We should never operate the equipment in that gap, either this lower side and a higher side. So, we need to design, or otherwise this temperature distress gap need to be minimum, or we should not use a one metal or one additive. We may use a composition active group for the physical absorption at the low temperature, another group at high temperature. So, two different groups are used. In that case, quite possible there will not be temperature distress gap. It can be without that gap. Now, some mechanism is specified as mentioned on this slide. We said during each contact, the contact layer is rubbed off. It is nothing like that where is stopped completely. It is getting rubbed off. That is why we are using the word boundary lubrication. And after rubbing off, it gets exposed to another corrosive medium, or we say corrosive liquid or corrosive substance. In that case, a next layer will come immediately. So, it is again a dynamic process, rubbing off of lubricant layer and reformation of the lubricant layer on the surface. But in that process, what is going to happen? Slowly chemical additives is going to deplete. It is already reacted with the surface, it will get depleted. So, it is not as good as a physical absorption. What we say in physical absorption, there is no change. It can be reabsorbed again on the surface without much problem. However, in the chemical case, it has reacted, mid oxide layer is removed. Now, we require a new percentage or some additional percentage for the next reaction. So, what we can say that whenever we are thinking about the chemi absorption, lubricant additives depletion we need to be accounted. It will get depleted with the time. It is nothing like that once you add lubricant additive, it will survive forever. It has a certain duration. After that duration, that lubricant additive will be depleted. You need to refurnish that, right? And this point says clearly, and they need to have one good balance, good trade off. They should be active enough to protect the surface, but should not be active, too much active, so that increase the corrosion rate or the high alarmic rate. Now, if I compare dry lubrication, I compare boundary lubrication by physical absorption, or we compare chemical absorption. So, we can compare on wear and sliding distance chart. We studied the wear rate. We know that as the sliding distance increases, total wear volume will increase. Wear rate we are not talking, we are talking of the total wear from the scratch, how much wear has occurred. If I plot this, First, this line is clearly showing Archer's law. In dry condition, they are in proportion. Sliding distance and wear volume will be having by and large linear profile, linear variation by and large. Now, when you come to the mixed lubrication, we come to the chemi-absorption, a chemical layer, then there is also loss of loss of the metal surface, because the additive is reacting with the metal. When it is acting with reacting with a metal, that means a fraction of that metal is also getting removed from the surface. How fast and how slow, that will depend on the chemical composition of the additives and the material, that can be decided, but generally that is a non-linear. It is not as linear as the Archer law states. You can see here that wear rate is lesser, wear volume is lesser compared to the dry case when comparing it, but it has a non-linear profile. This gap may increase, may decrease, depend on how fast the distance has been traveled. If it is a very fast, there is a possibility it goes down, it goes up also. And this is shows up with the physical absorption. We know the physical absorption case, most of the time the wear of the lubricant layer is happening, detachment of the lubricant layer is happening. It is not reacting with the substance, it is not reacting with a component, it is not reacting with a material. Naturally, wear rate in the case of the physical absorption will be lower than chemi absorption, whatever the situation. In that case, if I treat without considering the temperature or without accounting the temperature, in that case I will be getting always this curve. However, if I think from other side, say that physical absorption will not work when temperature is high, then in that case physical absorption case, whatever I am quoting here, it will turn out to be red line. Or say that these two will not occur simultaneously, that is why they should not be compared. Temperature will be always there, temperature factor also always need to be accounted. So, whenever physical absorption happens, chemical absorption should not happen. Whenever chemical absorption happens, physical absorption should not happen. There need to be have two separate situations. If I compare, I may get wrong results or wrong conclusion. So, that is why we use this kind of curve. We say this is dry mineral oil without any additives. It shows a better performance compared to the dry lubrication, because there is a lubricating oil and is cool the surface, distribute the stresses equally. While coming to physical absorption, there is a fatty acids. You can see clearly there is a transition temperature T here. Beyond that temperature, fatty acid coefficient of friction is increasing substantially. Now, if I neglect the, or if I use some sort of lubricant additives where the temperature gap is not there, it is acting instantaneously. Wherever the fatty acid is failing, EP additives or EB lubricant, or we say that extreme pressure lubricant is acting immediately, and that is why I can see that coefficient of friction is constant, it is not changing, or we say that EP additives are ineffective at that temperature. A lower temperature, they do not have any chemical reaction with the surface, but as this temperature increases, they are going to react with the surface. That is why I mentioned in my last slide also, whenever we make a lubricant, we generally add chemical related to physical absorption, chemical related to chemi absorption, and EP additive is another form of chemi absorption. We say that it is happening under the high temperature and extreme pressure. If pressure is very high, temperature will also increase there. So, they are related, or chemi absorption phenomena can be said as extreme pressure phenomena. So, overall if I want to make a lubricant, a good lubricant package, I will be using mineral oil or carrier fluid with fatty acid plus EP additives. So, overall package gives a satisfactory performance to us. It gives a low coefficient of friction compared to pure base oil, compared to EPA additives and base oil, compared to fatty acid and base oil. Overall package need to have all together. So, whatever the transient case, if the temperature is going very high, EPA additives can react. Otherwise, they will remain silent, they will not work, even though the cost is increasing by delta. But overall we need good result, and there are always uncertainties in machines. So, if the local temperature is going beyond certain temperature, then EP additive should work. Now, we say that what are the desirable properties from a boundary lubricant. I am talking boundary lubricant from the both the point of view is the physical absorption as well as chemical absorption. We say that need to have a dissolubility in the lubricating oil. If they are not able to get dissolved in the lubricating oil, they do not have any use. If they are not thoroughly getting mixed, then there is no use. If we are able to see additive separate, lubricating oil separate, then it does not have much utility, right. And it should be able to resist the penetration of the surface asperities. When this one surface asperities is approaching to other surface, these asperities should be covered with the lubricant additives, so that it is not getting touched or is not coming in direct contact with the surface as far as possible. So, in that case where will be in mild region. If they are asperities are able to penetrate in other surface, then where volume will be increase, where rate will increase. So, that is why we prefer to use a long chain alcohols for physical absorption, amines or fatty acids. These are all three are for the physical absorption, chlorine, phosphorus, sulfur or for the chemical composition. Above all, as we discuss in a friction chapter or friction lectures, that we need to have low shear strength of the interface. If interface does not have a low shear strength, whole tribology comes to 0, it does not have any use. Then we need to make interface having low shear strength, and that is necessary condition for using any lubricant. If they are this kind of boundary additives are not able to give us a low shear strength of interface, then does not have much use. So, that is why you need to have low shear strength, either directly getting attached to the surface or when chemically attaching the surface. In addition, what we can demand, we say that high melting point, they should not get disturbed as the temperature increases. So, if physical addition or physical adsorption is able to sustain up to 250 degree to 300 degree centigrade, that will be preferable choice. In that case, we are not going ahead with the chemical absorption, because we know chemical absorption is going to corrode the surface, lubricant additives will get depleted and we need to refurnish the lubricant. And as finally says that it need to suit the metal which we are using. Here the word you are using the metals, because mostly this kind of additives are effective with the metals. They are very less effective with the polymers and the ceramics. This is an example, it shows a stearic acid which is boundary additives. It has a melting point around 69 degrees centigrade when we are talking about the absolute without any reaction. However, when it reacts with the copper surface, copper stearate, it melts at the 120 degrees centigrade, which is relatively higher compared to 69 degrees centigrade. Similarly, if there is a chloride or a chlorine available as chemical additives which goes ahead with the chemi absorption, then iron chloride, which as a solid form as a sacrificial layer, temperature is very high, the 649 degrees centigrade. That means this can sustain above 500 degrees centigrade temperature without failure. However, if you want to further on the higher side, then sulfur should act. We say the iron sulfide, which will melt at the 1170 degrees centigrade, gives a very high temperature. They can be used as a high temperature additives. They are giving good results at the high temperature. However, we know very well the pollution is an additional consideration. Whenever pollution comes, or we have to think about pollution, we need to discard chloride, we need to discard sulfides. So, overall we can say the physical absorption should give a future or will be a better for a future compared to chemical absorptions, right. Now, this slide shows because there are I found some discrepancies in the books. People or researchers have written a boundary lubrication separately and extreme pressure lubrication separately. I am just trying to compare over here. We say that boundary lubrication as per them is restricted to the system where there is a thermodynamic reversibility. That means attachment and detachment. It is thermodynamically reversible. At a high temperature, lubricant will detach. So, this is what they have quoted, that boundary lubricant should be named if there is a thermodynamic reversibility. If there is no thermodynamic reversibility, which mostly happens in chemical absorption cases, in that case we should not be calling that the boundary lubrication, they should be called as extreme pressure lubrication, because this kind of mechanism acts under high temperature, and generally high temperature occurs because of the high pressure. So, what we say in this case, there are three examples: chlorine, sulfur and phosphorus. They act with the surface and they are known as a EP additives, EP lubricant. They are ineffective, or these all three are ineffective at the low temperature case, low load and low temperature case. So, interesting point to be noted for here, that people say this is a low optimization. Wherever I need lubricant from, EP additives are able to form it. Whereas a high temperature, we require lubrication, a factor lubrication, which can be sustained there for some time, and EP additives are able to make it. So, that is going to give us, or this kind of additives are giving an optimum performance as per the requirement. Wherever it is required, it gives. It does not make lubricant film everywhere. If the gear pair is coming in a contact, wherever the contact point comes, lubricant film is made that point there, because of the high temperature, high pressure, and corrosion occurs for some fraction of second there itself. However, it is clearly mentioned here that they have a good properties, they are nice, they are favorable from a commercial point of view, but from society point of view, they are not encouraged. They are carcinogenic nature, they are harmful, they are polluting environment. That is why there is a problem. Interesting story about this is that in a common petrol, sulfur will be there, and sulfur acts as a chemical absorption agent. It can react with the surface, it can make a lubricant film, and that is going to give us a protective layer, that is useful. But because of the pollution, now it has been emphasized the petrol should be free of sulfur, or it should be below certain limit, or the sulfur percentage should be minimum to this percentage. It is costly in twofold. First, you require process to separate the sulfur from the petrol, first thing. Second, you require some lubricant additives to be mixed with the lubricating oil, so that surfaces can be prevented from the wear. So, because of the pollution picture or pollution consideration, cost is going to increase. That is why we have always a problem whenever we use this chemical absorption techniques, then it may survive for 5 years or 10 years, and after that environmental issue will come, again we have to remove and think something else. There is a comparative study with between these three kind of lubrication mechanisms, which are dry, zero lubrication, or maybe say whatever the naturally formed layer on the surface. Second, boundary lubricated, which we are studying in this lecture, and third, which we will be discussing maybe in next lecture, that is a boundary that is a fluid film lubrication. Surfaces are completely separated by the fluid film. If we plot curves for these three conditions, one for dry, second for boundary, third for the fluid film lubrication, then what kind of curves we get for the wear rate? If I plot wear rate with the time, as the time increases, this is clearly showing a bathtub curve. Wear rate decreases, remains stationary, and then goes up after certain duration. Well, in boundary case, anything is possible. You say where it is decreasing initially, it reaches to one point, after that it can go and merge with 1 or can merge with 3. That means, if the surface roughness has decreased substantially, boundary lubrication may turn out to be full film lubrication mechanism, or if the surface is disturbed, irregularities have increased, it can go and merge with the dry case, or boundary lubricant will not be effective in that case. So, both the possibilities, and that is why we say many times whenever we are buying any new car or new automobile, we need to operate vehicle at the lower speed. So, this boundary case is over, or second comes and merges with 3. Then after that only we should operate at the high speed. Now, there are 2 other curves also. We say that wear rate versus load. As the load is increasing, even the full flame lubrication can sustain up to certain limit. Beyond that, it is going to be a boundary lubrication, and further if the load is increased further, then it may merge with the dry lubrication. Or in other words, as the load is continuously increasing, lubricant may not be retained at the surfaces at the interface. It will be simply squeezed out from the surfaces, and if there is no dynamic load, if there is no reversible position change, then lubricant will not be sucked back. It will be simply moved out. Whenever the lubricant comes, it will be simply moved out of the interface and we will be getting very high wear rate. We say that every lubricant need to be designed as per the load. For high load, we will be designing different kind of lubricant. For low load condition, we will be designing different kind of lubricants. Coming to temperature, which has a more or less same factor or same effect as a load. As the temperature increases, we know that detachment from the surface will increase. Even for chemi absorption case, the temperature is supposed to be very high, then rate of the wear will increase because of the more and more reaction with the surface. So, that fluid film lubrication is merging with increase in temperature to boundary lubrication, and beyond certain temperature is merging with a dry lubrication case. So, this comparative study indicates clearly whenever we design a system, we should keep in our mind for how long we are want to operate it. If for the longer duration we want, we should operate under some condition which gives a favorable surface condition to the equipment, and then it should be operated under other condition. Same thing, if we know surely what kind of load is going to come and how much load is going to come, then we should design boundary additives or boundary lubricant or fluid film lubrication mechanism accordingly. So, I'll just cover one experimental study which we did in our lab, and results are related to our boundary lubrication mechanism. You can see this figure has a eddy current dynamometer which applies a load, and the load applied in this case is from 0 to 75 Newton meter. There is a torque sensor which can measure how much torque has been applied. And what is this is a gearbox which is a test box where the gears are going to get tested. There is a motor to drive the gearbox. So, we are using both the things. We are using motor to drive, we are using dynamometer to stop or apply the load. We are using both the combination, and torque sensor to measure how much torque is been applied, and there is a display unit over here which will give a display of the torque. What we are talking the gearbox is a 2:1 ratio. We say that pinion gear has a 22 teeth, while gear number of teeth on the gear are 44. So, this at 44 divided by 2 and 22 gives us 2:1 ratio, and they are standard involute profile having pressure angle 20 degree, and module is defined as a 2.5. We to find out online or we go ahead with the online measurement, we use sensor unit, what we know as an online sensor instrument. You can see there is a oil conditioner sensor. What is the meaning of that? Oil will get disturbed, oil will change quality continuously. If it is getting more and more acidic, then the tan number will decrease and that tan number will increase. Similarly, there is a possibility of corrosive wear. So, there is a moisture sensor. Moisture sensor clearly indicate if the relative humidity is very high, then we should not conduct the experiments because a major governing factor will be corrosion, and there is a mechanical action. So, there will be a corrosive wear. However, if we want to do corrosive studies or we want to do a study on a corrosive wear, then we should be able to use with some water environment, a higher moisture environment. Above all, there is a one unit what we say as a total ferrous wear debris analysis sensor. It is generally finds a iron particle, how many iron particles are getting circulated through the lubricating oil. So, it gives us an indication of wear rate. Higher the number of particle, higher the wear rate. That is why this unit is useful when it get attached with this test setup, you can see there are number of tubings going from this, and these tubings are connected to this unit. You can see the tubings are here. In previous slide, here tubings are going and the unit is placed somewhere here. So, it gives overall reading to us. Let us start with some experimental readings. We say that we bought a new gearbox, and we know whenever the gearbox is new, it should not be loaded completely. So, what we selected almost 0 load and 500 RPM speed. So, and is given in RPM, that is a 500. I will not use a unit over here because RPM is common unit, and torque as a 0.35 Newton meter. We did not have applied any torque from the dynamometer, but we know that during assembly there will be always some sort of misalignment. There will be some resistance from assembly, and that is given as a 0.35 Newton meter as a torque. We have not done anything purposefully, but it is coming because of assembly, and this gives a iron percentage or iron concentration in ppm. Number of experiments, and this experiment was done in lubricating oil. I would say the ATW90 is a motor oil, and it has a good EP additive package. This kind of experiment happened, and whatever the experimental result what we got is that shows a relative humidity ranging from 45% to 55%. That means, it is not going beyond certain limits. We can conduct this kind of experiments without much problem. Just after doing experiments, just starting experiment, we took the reading and we found that the 74 ppm as iron percentage or concentration. After 2 hours operation, this percentage increased to 84. After that, it remains almost steady 77, 73, 69, 65. Interesting thing is that when we do this kind of thing, it is always in our mind. After that, if I want to operate, this percentage should come down, because bathtub curve says clearly initially where it will be high, subsequently it will come down, but it did not happen to us. We increase the speed from 500 to 1000. You can see the minimum weight, this is in sequence. After operating of the 10 hours, 11th hours was with this speed. They are in sequence, all these experiments are in sequence. So, this is 11th. This shows a 65, while this shows a 66% is increasing. Of course, there will be always some inaccuracy. So, we cannot differentiate between 65 and 66, but as we are increasing more and more number of operating hours, we are finding more and more particle percentage coming in this. Either there is not a filter system is not working well, or something else is problem, or another possibility is that the high temperature, high speed means high temperature. At a high speed, there is some flush temperature is happening, or chemical additives or EP additives are reacting with the surface. They are corroding surface, and then they are removing the top asperities. That is why the percentage is increasing. To confirm that, we increase the speed also, say from 1000 RPM to 1500 RPM, keeping almost the same load, no change in the load as such. This is happening because of the misalignment or some inaccuracy in the surface. Now, what we are getting over here, this percentage is continuously increasing. This means more and more corrosion happens to the surface, or even though we know the gear lubrication mechanism or this lubricant additives is known to be one of the very good gear lubricant, and still that we are getting this kind of wear particles. That means, the gears will never work in hydrodynamic domain, it will never work in fluid film lubrication mechanism, working in a mixed lubrication or boundary lubrication. That is why we are getting wear particles, and the particle percentage is increasing with increasing speed. If the mixed lubrication case, percentage will not increase, it will come down. So, that is why we feel that this kind of experiments are showing the results related to the boundary lubrication mechanism. Let us see other results. Second set of results, after changing the oil, we have changed the lubricating oil here. So, that all old particles whatever were getting dumped in the lubricating oil have been removed. Fresh oil. Fresh oil, we are getting good readings at the 500 RPM. You can see 43, 36. In other words, we can say it has reached to steady state condition, or running in period is over for 500 RPM. but it should continue for the 1000 rpm also, 2000 rpm also. But what we got when we are operating at the 2000 rpm, we are getting different environment, we are getting different results. You can see 89 from 36 it jumps to 89. After operating for the 7 hours, when you are operating that equipment for the 8th hour, we are getting 89 ppm. That is much higher, almost threefold compared to 36. And this percentage is increasing to a certain limit, and after that it is decreasing. To get a confirmed results, we operate at the one higher speed further, and we can find there is a unbound lubrication, unbound ppm level from 219 to 658. That means more and more temperature is getting induced at the surface, or some sort of load is coming on the surface, which is creating a higher number of particles. However, the stock sensor clearly indicates that a misalignment was not that dominant. It is only the speed which is changing the phenomena, and it is giving higher wear rate. Now, I can think in a different way. I can say that when the speed is increasing, vibration level is increasing and load level is almost 0. So, additional vibration phenomena is happening, and that is going to increase the fatigue failure, or is the fatigue wear is going to increase with increase in speed. To confirm that, what we did, we applied a load, so that the vibration phenomena can be reduced, the vibration amplitude can be reduced. Even for high speed, it should not vibrate that much. So, okay, so before that we say that conclusion from this slide, the changing operating condition changes the dynamics of boundary lubrication layer. It is continuously changing, it is not a stationary. 500 rpm, it is showing a steady state condition, but when you are switching to 2000 rpm, it is showing high wear rate. As I mentioned, one possible reason is a vibration, continuous or periodic loading, and that is going to induce fatigue failure in a surface, or at least the top asperities are chopped off. So, we need to confirm that with a load. If I increase the load, what is going to happen? And okay, so before that we try to find out particle size, what is the range of particle size, to diagnose whether particle size are minor size or under mild wear domain or severe wear domain. And interestingly, we find too many particles for the size between 5 to 15 micron. But interesting thing, this number of particles are continuously decreasing with the time. That means it is going for the betterment, it is going for the convergence. Continuously number of particles are decreasing. Coming to 15 to 25 micron, again the number of particles are continuously decreasing. So, that is a favorable situation. We can say starting case it may be severe wear, but it is still in controllable case. It is moving toward the mild domain or mild wear side. And interesting thing is that we found couple of particles having size more than 100 micron, and when we studied mild wear and severe wear, we say that about 20 micron particles, it is a severe wear. So, most of the domain case in this case it will be the severe wear, but they are not uncontrollable, they are controlled, they are moving to the right direction. That means, we do not have to worry too much, and we know this is running in time, is a bedding in time, where particles will be larger initially. This is for the 500 rpm, same thing was done for the 2000 rpm also. What we find again the same thing, that number of particles are decreasing, except for this case number of particles are decreasing, which are in a range from 5 to 15 micron, and there is no particle size, no particle which has a size greater than 100 micron. That is a favorable case. In all other cases also we find that particles are decreasing in numbers. So, these are the favorable situation, their bedding in time is going hard. If you want to reduce the wear rate or reduce this kind of particles, then we should apply load, and that is why we did experiment with the load also. Say rpm 200, torque applied load is a 5 Newton meter, wear rate or number of say ppm level is continuously decreasing, the 152, 154 is coming to the 107. Of course, 2-3 ppm I am assuming that is inaccuracy, or it is not giving that much reliable results. Now, if I increase the load, what is going to happen? See, I am increasing the load from 107, it is coming down to 100 and continuously decreasing to 69. That means, load is working, whatever we are thinking, the vibration is creating some problem, is photic failure or related failure of the related wear because of that is happening over here. Now, if we increase the speed and the torque, again we are getting a lesser number of ppm or lesser ppm in this case. Same thing, same results for the 800 also. 800 and at load is higher side at 20 Newton meter, it comes to results now 32 Newton meter. That is indicating, that is showing that bedding in time is coming to the closer or almost negligible level. After that, we could not find any further improvement. This clearly shows the number of particles, the ppm level is reaching almost 30 ppm, and beyond that we are not able to improve. Whatever the load condition, whatever the speed we are applying, that remains on the situation. Or in another word, if the load is applied, results are good. Now, here we have removed the load also. We have brought the torque almost to 0 level. Of course, I am not using the word 0.3 Newton meter because all the torques are very high compared to 0.3, 0.4 Newton meter. That is why we put value as 0. And this is the 0 torque and 1000 rpm. Still, we are getting good results now. That is a complete bedding in completely running in time. We say the running in behavior. Now, what is happening? Why vibration does not happen at 1000 rpm? Now, we can say there are a number of asperities which were earlier there, they have completely got flattened or torn away or removed from the surface, and there is a some now marginal lubrication keep coming. We say that there is a fluid film lubrication with some boundary lubrication. There is some percentage of boundary lubrication and major percentage of full film lubrication. That is why the gear wear rate is low in this situation. That is a favorable situation for us. We say that when we study this boundary lubrication mechanism, we are able to understand the mechanism in a different manner. We say that even though we know the bedding in time or bedding in behavior, the wear rate should be very high initially, it should reach to steady condition and after that it should increase. While in this case bedding in time, it shows that even though running in behavior is changing with the speed and changing with the load condition. That is why we need to understand system completely. If there is a possibility of a light load that is introducing the vibration, we should not introduce, and that is a typical example for the rolling element bearing. We say whatever the dynamic load capacity of the rolling element bearing, we should never apply a load lesser than 3% of that. Reason being, there will be more clearance and less load, less deformation of surface, that will cause a more vibration, less load carrying capacity, and pitting in that case will be much faster compared to with the load. In other words, what we say from Archer law, as the load increases, wear rate will go down, but when it comes to the lubricated case, when particularly the boundary lubrication, we are saying it is not the case. Quite possible increase in the load may decrease the wear rate. It is not in that proportion itself. With this, I complete boundary lubrication mechanism. When next lecture, we will be discussing about the mixed lubrication mechanism, where we will be thinking about some portion of the surface undergoing boundary lubrication and remaining portion is undergoing hydrodynamic or elastoaerodynamic or some other lubrication mechanism. When talking about some other mechanism, it may be a squeeze film lubrication mechanism also. Thank you for your attention.